and further we can more effectively. To realize all these applications, we need to invest in R&D as well as in development of this robust and reliable infrastructure that can support quantum communication in satellite systems. As discussed, some projects are going on in collaboration with ISRO on space-based QKD systems to develop indigenous technologies. We need to work towards standardization also so as to ensure interoperability and widespread adoption of the technology. Application of quantum communication in satellite are vast and promising. It is up to us to harness the potential of this technology for a greater good. I believe this conclave would work as a trigger in accelerating the research, development and deployment of quantum communication in satellite system. The knowledge and expertise of all the participants in this conclave will undoubtedly contribute to identify the opportunities and challenges in the field and finding solutions to them. Let us take this opportunity to collaborate and share our ideas, experience and best practices to pave way for the widespread adoption of the quantum communication in satellite system. With our collective efforts, we can create more secure, efficient and sustainable future for satellite communication and leverage its potential to address most of the pressing global challenges. Thank you very much.
Thank you, Honorable Chair. And now I request Professor Joyee Ghosh to present her keynote address. She is an associate professor in IIT Delhi and heads the Quantum Photonics Research Group in IIT Delhi. She's playing active role in quantum technologies projects sponsored by DRDO and Department of Science and Technology, and is also a distinguished expert member of National Mission for Quantum Technologies and Applications and the Joint Quantum Communication Working Group. I would humbly request all the esteemed panel to kindly adhere to the timings as we are very tightly packed today. So it's 10 to 15 minutes for each panelist. Thank you so much.
So a very good morning to the audience here. It's a pleasure and honor to be here in Vigyan Bhavan. It's my heartfelt thanks to the organizers here for inviting me. Thanks a lot. So today I'm going to speak about entangled photon sources, quantum photonic sources that we are building in our group in IIT Delhi. And we have projects both in free space as well as fiber-based quantum communication. So just before I go on to those projects and the results from our group, here in a nutshell, I just wanted to highlight the kind of things that we do in our group. So the broad-based research interests are quantum and nonlinear photonics. We also explore atomic physics, light matter interaction, and basically we are interested and our challenging projects are all based on quantum technologies with single and entangled photons. Now there are different endeavors in which we work on. So these are the two blocks that I'm going to detail on today as far as allowed the time. So one is a fiber-based quantum communication project funded by DST Quest, and the other one is a free space quantum communication project funded by DRDO. We have other interests, so these are based on entangled photons, single and entangled photons. We also have interest in quantum detection via squeeze light. So we are cranking up our experiments for the generation of squeeze light. We are also interested in silicon nanowave guides, again for the generation of correlated photons, and we explore silicon nanowave guides for the same. A little different from all these aspects are coherent light matter interaction, where we explore atomic vapors at room temperature, and we wish to see experiments that can be applied towards quantum storage, quantum memories, but there's a way to go in that direction. So here's the group and few pictures from the lab. It's a, sorry.
The other one. It's not
The red one. Sorry for this. Yeah. So it consists of PhD students and a couple of postdocs. We also heavily collaborate and share the group with Professor Vivek Venkat Raman. So coming to the main aspect of the talk, so as we all know, quantum photonic technologies are very much interesting, particularly for their applications in quantum communication that require, and that's due to their speed, robustness, and ease of implementation. Now there are and in this regard, single and entangled photon sources are very lucrative. Particularly, it's important to develop efficient sources of such photons. Now there are two directions to explore this. One is fiber-based quantum communication that utilizes photonic qubits and sends information from one location to another through optical fiber links. And these are particularly preferable when you're looking for high bandwidth, long distance communication, as well as experiments which is shielded from the external environment in order to minimize electromagnetic interference. The other, so this one, these are based on detectors and sources which are pretty well developed. The detectors which are solid state like in-gas SPAD, they are not as efficient, but today we have SNSPD detectors, as we all know, which are pretty much efficient as well as expensive. On the other hand, free space optical communication relies on the optical band of 700 to 850 nanometers. This is the near IR band, and here again sources and detectors are well developed. Single portable single photon detectors are more efficient than what we get in the telecommunication band. And we also have SNSPD detectors, which are definitely expensive, but they are also very, very efficient. So we have projects in both these regimes. And before that, I would just like quickly to focus on this slide. There were many speakers yesterday, so I am not elaborating on any introduction here, but just want to focus on one small thing, that there are several QKD protocols, quantum communication protocols, that can be broadly classified under two umbrellas. One is the prepare and measure based protocols, which are single photon based protocols, and in particular BB84 is very popular there, as we all know. Many of the experiments have been utilized using attenuated laser pulses, but these are prone to attacks like photon number splitting or intercept and recent attacks. In order to circumvent that and in order to make your communication link more secure, it's important to reap the benefits of entanglement. So you have entanglement-based protocols. There are two kinds, the Eckert 91 and the BBM 92. There might be other versions of that. And these are particularly lucrative. Why? Because these actually utilize true single entangled photon sources, which are quantum sources. These are resilient to eavesdropping attacks. They are inherently random. They offer long transmission paths, and they also inherent source independent security. They offer, so in this direction we like to explore entanglement based quantum communication, and these are details, because the source, the entangled photon source, could be in the middle between the sender and the receiver, or it could be on either side of it. Now, the first project, which is our project funded by DRDO, this explores free space quantum communication. So the task is to set up free space optical link, and the initial task is to develop an efficient source of entangled photons for the same. So this is particularly important for areas or locations where fiber installation cannot happen, or it's difficult to install fibers, let's say, and therefore have fiber communication, and particularly interesting for moving terminals, including the important aspect of satellite-based links. Now, this is the task, but the problem is, especially when you're doing, even for the simplest of quantum transmission, you would need some kind of a shared reference frame between the sender and the receiver. Now, in standard quantum communication, utilizing photons, the popular idea is to utilize polarization qubits. Now, polarization is about, so the sender and the receiver on each end, they need to align or orient their axis very carefully with with respect to the H and the V, because polarization information is about H and V. So that axis orientation is very important, and also to have a relative orientation between the sender and the receiver. This is all fine, but if the two parties are moving with respect to each other, or there is some rotation or some misalignment, then this kind of an information might get distorted when it is being transferred from the sender to the receiver. In order to circumvent that problem, it's important to encode your qubits in rotationally invariant hybrid photons. And with that aspect, we have this project where we actually explore an alignment-free QKD, or a quantum communication protocol. We are in the middle of our experiments. We have achieved polarization entanglement in this, but it needs the results need to be improved. And the next steps are hybrid entanglement based on multiple degrees of freedom of the photons, such as orbital angular momentum and polarization. And then once that setup is ready, we are going to explore it for entanglement-based QKD. So these are our recent results for polarization entanglement. The other project, which is funded by DST Quest, actually explores fiber-based, all fiber integrated, fiber-based, WDM-based source, a waveguide-based source. And these are important, particularly if because these systems, any kind of quantum communication or any of these quantum technological experiments are becoming more and more complex. So it's important to have stability and high efficiency in the source. And in this regard, integrated systems, as there are other speakers who talked about it yesterday, integrated systems utilizing fiber-based or waveguide-based systems, they have demonstrated a huge potential. And in this regard is our second project, which is totally fiber-based, and it motivates, or it wants to explore a multi-user QKD kind of a protocol. So recently we have built our source. It also got highlighted, and so it's not only important to have an entangled photon source, but it's also important to have a source which competes with other similar sources internationally. So that depends on the characterization of spectral brightness, the coincidences to accidental ratio, and all of that. And we are proud to demonstrate that we have such kind of a source which is very compact in our lab. We want to put it in a box and then explore it towards multi-user QKD. So we have so this is highlight, and recently we have also actually seen polarization entanglement with this source, both in broadband as well as the individual channel entanglement. This has been achieved, and the next steps is to explore entanglement-based QKD in the same setup. This is a very compact tabletop setup, and such sources can be taken outside the lab and soon explored. So I would just like to, so those are the experimental endeavors, and we also actually explore a lot of designs on integrated architecture that, for example, generates all optical Bell states through a multipole integrated waveguide device. So these designs are all in popular nonlinear materials of KTP and lithium niobate, and as you all know, if we can have such architectures, if we can fabricate them, we can actually generate all the 4 Bell states through such an architecture, or we can also generate post-selection free hyperentangled photon pairs utilizing such an architecture. Hyperentanglement is again utilizing different degrees of freedom, and I will not go and get into the detail, but I would just like to highlight here, we are not fabrication experts, but if such fabrication of such devices are possible, keeping in mind all the practical aspects, then we can have these sources very compact, almost on chip, and we can take it out to space as well. So this is one direction, and just 2 more slides here. So I would just like to highlight, because the group also explores silicon nano waveguides, because we want to also explore correlated photon emission through silicon nano waveguides. Silicon is very hot, very easy to implement, also because of the CMOS architecture that is very compatible with silicon, and we are developing such sources as well, and we are trying to crank up our experiments on this. And so this is a slide that we have where our recent paper in PR Applied was actually selected as the editor's suggestion, which talks about broadband silicon photon wires for broadband polarization entanglement at telecommunication wavelengths. So yeah, yeah, those are the experiments, and yeah. Thank you.
Thank you, Professor Ghosh. Our next keynote speaker, Dr. Ravindra Pratap Singh, is the chairperson of Atomic, Molecular and Optical Physics Division at Physical Research Laboratory, Ahmedabad. He built experimental program in laser physics and quantum optics from scratch at RPRL, Ahmedabad, that houses three 10,000 class clean labs with equipment and accessories of more than $5 million. He is presently involved in free space quantum communication projects from Department of Science and Technology and Department of Space as part of Quantum Science and Technology program at PRL. Dr. Ravindra Pratap Singh, please.
Thank you for the introduction. It was very generous introduction. I think that I didn't give. Maybe you might have taken from LinkedIn. I gave only one line introduction. That was good enough. Anyway, thank you for inviting me to be here, giving this chance. Department of Telecom, Mr. Abdul Qayyum, Mr. Venkatraju. So, I am here talking to you because of my students and younger faculty colleagues. You can see them, they are good numbers and there are many more. So I have given names who are directly contributing to this work. So Ayan is now in UK, working in University of York, postdoc, and India is in NUS, Singapore, and Rupesh is again, he is from lab, he has become faculty at University of York. And Pooja is electronics and communication engineer, so they equally contribute and they contribute heavily to the quantum communication program, electronics and communication engineers. Jabir and Nizil, they are at NIST, and Ali is in Fraunhofer Institute, and Ali is in UK, Fraunhofer Institute, Sarika is in Germany, Fraunhofer Institute. Anju is doing PhD, she is working on CVQKD. Okay, already we have some results on CVQKD, and Samantha, Sasi, they are my younger faculty colleagues. So, in PRL, many people don't know, that's why I put PRL, this t-shirt today. So, it needs a little bit of advertisement. People think PRL is in Delhi, many people get confused. Everybody knows ISRO, but they don't know ISRO came out of PRL. Okay, PRL is 75-year-old institute. And whole space program is started from PRL. They don't recognize PRL, many people. They don't take even name of PRL, but it's all because of PRL. You see this, all the satellites and all. Even first satellite, Aryabhatta, was assembled in PRL. It started from PRL only. So at PRL, we have started this quantum science and technology program. We have like covering all the stacks of quantum technology, starting from communication, computing, sensing. So we are covering all the technology verticals in quantum. This moving is taking.
The big green one. Yeah.
That side or this side I have to do?
No, the big green is one.
This
Yeah,
one?
you don't.
Oh.
That's, I had the same problem.
There's so many greens. There are 3 greens. So, as you see this QKD, we are going to talk about QKD. So, it is like discrete variable, continuous variable, and we are covering whole reason. So, you can have prepare and measure. Already Joyee has talked about B84 and B92, prepare and measure. You prepare in a particular polarization state or even phase, particular, and then you measure. And then entanglement based protocols, BBM92 and Record 91, and then accordingly, in continuous variable, you have again prepare and measure and entanglement based. You can have Gaussian modulation or discrete modulation. So, all the things you can cover. It's going, no?
The big green one.
Yeah, big. Oh. So, this you can have, as I told, entangled photons as well as prepare and measure weak coherent pulses. Joyee has told that you attenuate the laser so that per pulse you use pulse laser so that per pulse you have less than 1 photon. So it's not single photon source. Many engineers get confused. They say single photon source, single photon source. When you say weak coherent pulse, it's not a single photon source. Single photon source has very peculiar characteristics, which is not possessed by this weak coherent pulse. So it's attenuated laser, pulse laser, so that on average per pulse is having less than 1 photon. So both are different things, single photon source and weak coherent pulses. So you can use weak coherent pulses as well as this entangled photons. So this is when you are using entangled photon, this is there are two ways. One can do satellite-based quantum communication. When you are using entangled photon, this is pair. You can use it as trusted node. Satellite can be used as trusted node. And when you are, because you are not keeping the key in the satellite, that's why it's trusted node. You are not keeping the key is here only. And when you are using weak coherent pulses, you generate key with one station, then you generate key with another station. So both keys are you can see that both are there. So now this is K and KP, both keys are there. Then you XOR and then you send and then again another XOR, and both these stations are having same key, symmetric key distribution you can do, and that's how you encrypt the message and you can have secure communication. So you can have both trusted. Here it is trusted because satellite is having key. Anybody can hack, but you have to trust that nobody is hacking. So that's why it's called trusted. Okay, you are trusting that nobody is going to hack. This is called untrusted. So both ways you can have, and my heart goes for this entanglement based, okay, because it's untrusted. And if you want to develop quantum communication network or QKT network or internet, quantum internet, it has to be based on entangled photons only. So that's why one should have this one. So we proposed, like in 2015 it all started, we proposed for satellite based quantum communication to the principal scientific advisor with all the budget, timeline, everything, but it was not moving. Then Quest started, DST in 19. So we thought, let's go for this free space quantum communication, because this is the stepping stone for satellite based communication, basically longer free space quantum communication. So we thought we should go for free space quantum communication, and that will lead to satellite communication later. So that's how it started in 2019. So under this project, we have done quite a bit of work related to QKD. We have generated, like we have used BB84 for 200 meters free space channel, then entangled photons, and most of the results are published now. And we have studied like what could be the information leakage also, which kind of attacks are possible when your source or detector is not perfect. Okay, in theory you assume that everything is perfect, okay, and it's theoretically secure everything, but it's not always true, because your instrument, your equipment is having some imperfections, so it can't be secure like theory. So that we have done anyway. So this is the entangled photon source. It's very compact. It's like 15, 20 by 25 centimeter. Very compact. It is in the box, and it uses like periodically poled crystal, nonlinear crystal. And here you get two entangled photons. This is the pump laser 405, and it's degenerate. Degenerate means both the pair having same wavelength, 810 nanometer. And then you measure polarization correlation. So these are the like analyzer and lambda by 2 plate and PBS you use. So you analyze the polarization. You are looking for polarization correlation. Here we are generating polarization entangled photons. That's why you are looking for polarization correlation. You fix polarizer of one, polarization of one beam, one arm, and then you keep on rotating. So that's what this correlation curve comes. It's like interference, this correlation curve. Like interference also, it's field correlation. So now we are looking polarization correlation. So that's what you get. And so you can see that's this is the measurement of Bell inequality measurement. So 2.63 is a very good source of entangled photons and very robust also. So this is the schematic where we have done this free space quantum key distribution using entangled photons. We have done for 35 meter and 200 meters both. This is here entangled photon source sitting here. Then you send to Alice and Bob, and these are the cabins, and this is the where we send from Alice and get it bound. So that's what. So this is the similar curve which I was showing earlier. These are the 98% confidence interval lines, inner and outer. Middle one is theoretical fit, and then even after distributing at 200 meters, you can measure the Bell parameter is 2.54, and we collect the photons for 1 nanosecond. So that's what timing is very important. If it is 200 meters, around 200 meters, the photons which are coming, it is like you have to collect around this 648 nanosecond, even 0.5 nanosecond if you are, so you will not get the key. And because we are having HS plus VV polarization entangled state, so when you are sending H, it has to be measured in H, both has to be in H. And what is the beauty of entangled photons when you are using for QKD? You don't have to use random numbers. That's the very good advantage. Because entangled photons, they take care of the randomness, so quantum mechanical randomness. So that's the very good advantage when you are using entangled photons. So that's the key, basically. Anyway, so what is going? So we have to go back. How to? Yeah. Okay. So that's what you HHVV, you count this thing, a diagonal thing that will form the key. So that's the key rate. You can have this Cuber also 4%, and these are the parameters, the channel transmittivity and all those things. So then we have studied the atmospheric effect also. We have space and atmospheric sciences program in PRL. So we could find out the extinction coefficient, megameter inverse, and scattering coefficient. For PM, means particulates who are less than 2.5 per micrometer, so their concentration also we could find out. And what we observed that our key rate depends on these atmospheric parameters, and it follows like key rate follows atmospheric conditions. So what we say, if you are studying quantum key distribution, at the same time you can have atmospheric parameters, aerosols and other. So it's very great advantage. Same time you are having atmospheric parameters along with quantum key distribution. Nowadays climate studies are becoming very important. Atmospheric studies are very, pollution is a big problem. So along with that you get as byproduct. In fact, when I was presenting this work in Israel in a conference, in a meeting, they said, have you patented this idea? I told no, we have not patented. They were very impressed. That's really very good. You can, along with QKD, you can have like atmospheric data also. So this is the CVQKD result we have got already. We are having some results. This is, so we are getting around this one, secure key rate 0.30 bit per pulse. So we are using this 80 megahertz laser, so quite a high key rate. And why we use CVQKD? Because it's easy to integrate with existing communication network. You get, you don't have to use single photon detectors, which are very costly, very bulky. You can use standard photo detectors, homodyne detectors. You get higher key rate. Okay, so there are many advantages when you are going for CVQKD. So that's what it is, and ongoing work. So this is the discrete modulation, and that's what result was shown, and this is the setup, and this is in-house developed QRNG. We have entangled photon based QRNG. We are making random numbers using entangled photons. So this is, we are using that only for this work, because it's prepare and measure this discrete modulation. We are modulating, we are preparing in particular state. So you have to use random numbers. If you are using entanglement, you don't have to use random numbers. So that's why QRNG was used there. So this is the Gaussian modulation thing also we are doing. Okay. So this is the setup, and the let us come to the international scenario. So Chinese, basically they are the leaders in quantum communication, and all the major investment by countries, different countries, European Union, USA, and everybody started putting heavily into this quantum technology because of misuse, and we should be thankful to the Chinese for this big boom in quantum technology investment. Okay, we are here talking maybe because of this misuse 2016 launch. Okay, so and they have planned to have worldwide quantum key distribution network by 2030, and I am pretty sure they will have by that time, because already they have developed this network in China using 5-6 stations, and they have 3 satellites already. MISES is one, they have already 2 more satellites, and they are having QKD network over China using satellites. Then China was not the first one. Basically, this free space thing and long distance, it started in Germany, and they did it in, you can see that, in 13 itself, okay, using flight, 20 kilometers. They could do the key distribution, Herald Wine Further group. Then Japan, you will see that in May 14 itself, they launched this satellite. Although they published quite late, it didn't work for a very long time. That's why they were hesitant to publish the data. They published in 17 only, and they did B92. They got the key, okay, and published later. So they were the first one, rather, through satellite getting the quantum key distribution. It was very compact, entangled photons. This is very compact satellite, okay, macro satellite, and very compact ground station. Their ground station is the most compact one. And then Italy was the first one to show that it's feasible to use satellites for quantum key distribution, and they published in 2015, much before the Chinese launch. Yeah. And this is the future plan at Quantum Science and Technology program. So we have turbulence, how it is going to affect, how to mitigate the effect of turbulence. We can simulate uplink and downlink using calibrated turbulence cells that we have with astronomy and astrophysics division of PRL, and development of device independent QKD. That's what we are doing after this BBM 92. Then entanglement swapping and quantum teleportation. It has already been talked yesterday. We are doing that also. And then finally, using structured light, we can have like more robust and secure key distribution. And a new lab has started working to develop photonic quantum computing, because it is the best bet for quantum internet, worldwide quantum web. Okay, and with that, thanks.
Thank you, Professor Singh. Well, Dr. Bruno Huttner yesterday enumerated on the future of quantum communications. So we request him now to share his inputs in this session. We all know him as the Director of Strategic Quantum Initiatives in IIT Quantique, Geneva, Switzerland. He has extensive experience in the field of quantum technologies, particularly in the areas of quantum cryptography and quantum key distribution. He is also the co-chairman of the Quantum Safe Working Group organized by the Cloud Security Alliance. Dr. Bruno Huttner.
Okay. Right, so it's good to be back. Today I'm going to talk to you about basically randomness, and especially randomness in space, because that's the topic of the session. So, as usual, I like to go back first to basics, and let's think a little bit about randomness. And randomness is really the basis of all cryptography. If you want to exchange a secret or to do something which nobody else can know, obviously, you have to surprise him. You have to do something which is not expected. And that's why you really read randomness. So any good cryptography, it can be quantum, it can be standard modern cryptography like RSA, it can be post-quantum cryptography. Every single cryptography starts with random keys. Somehow you need to start with randomness. And then, of course, afterwards, you can have mathematics, physics, whatever, QKD, but you still start with randomness. And here I have to disagree slightly with my esteemed colleague. Even with entanglement, you need randomness, not on the value of the bits, but on the choice of the basis. So if you do a Bell experiment, you should still need some randomness to start with in order to make sure that the two bases you're going to use to measure are not the same. I mean, to make sure that they are random, basically. So whatever you do, you start with randomness. Now, what is randomness? I mean, it's actually very hard to know exactly what is randomness. You can basically test randomness, but it's much harder to really define it. And this was started, well, more than 100 years ago, 200 years ago, yeah, something like that, by Kerckhoff. And he said that in cryptography, in order to have security, what you need is a key which is, first of all, unique. So you need to make sure that nobody else knows the key. So you can have something perfectly random. If it's known by somebody else, obviously you cannot use it for cryptography. Then it has to be really truly random. That's the main thing, unpredictable. If somebody can know what will be the next bit of your key, obviously you cannot use it. And last but not least, you need to store, distribute, and manage securely. So if you got a best key, which was basically generated with random, distributed with random, but you store it badly, obviously you cannot use it anymore. So basically, cryptographic randomness has really to be private, so it has to be yours, and that's why we believe it's much better to generate it as close as possible to the place you're going to use it, basically locally. So it's not such a good idea to ask for a randomness source to be away and to send it to you in some way, because somebody can intercept it, find out what it is, and then of course it's still random, but it cannot be used for cryptography. So how do you build a random number generator? There are several steps, and I think here it's the easiest way, the best way is to go back to NIST, okay? And when you look at NIST, there are three different steps, basically. The first one is the entropy source, and this has to be a physical process in order to be secure. You need to have something which generates bits in a way which cannot be predicted in any way. Of course, being a physical process, it cannot be perfect. Therefore, you need to process it in order to make the bits as perfect as possible. And this is really the goal of the random bit generator, which you use to basically improve the randomness of your system. Once you have these two things, then you have a random source you can use. And of course, before you use it, you test it. And many people think that randomness is something that is only tested by all the NIST recommendations. That's not truly the case. You need to start from the beginning, generate random bits, process them to make sure they're as perfect as you can, and then test them. If you got a string of bits and you only test the randomness through the NIST process, through the NIST test, it's not enough because you don't know if somebody else can know it or not. You really need the whole process. And actually, the hardest part is the entropy generation. The rest is more or less well known. You can easily make a random bit generator. You can easily test strings of bits. I mean, you have ways to do that. To generate the entropy is what is actually the critical path. And here, how to generate this entropy, we can go back to John Neumann, who said that basically you cannot do it with deterministic systems. Okay, if you start with something deterministic, it will remain deterministic. There is nothing you can do about it. So never start with a pseudo-random number generator. You can use this pseudo-random number generator as long as you started with good entropy seed. Okay, so that's really the main thing you need to remember. You need a good seed to do that. How do you get this seed? Well, you can start with classical systems. And then if you work with classical systems, there are two ways. First of all, you try and get something with external noise. So some noise coming into your system, and you say, okay, this noise has to be random, and I can use it. That's possible. However, you need to make sure there are no hidden regularities. And basically, if you look at this graph, it looks random, but if you look at the frequency distribution, you will find out that it's not at all, for example. The second thing is that this random thing can be manipulated. Somebody can give you this. It looks very random, but the guy who is giving it to you knows exactly what it is. It can also be duplicated. It means that somebody else can be next to you, find exactly the same randomness. And of course, if you are in a remote location, for example, somewhere in a telecom house or something like that, you may not have access to external fluctuations. And therefore, it's not a really good idea to rely on external noise. So let's try and see if there is another way you can generate randomness from classical system. And there is a way which is quite used and probably not bad at all. It's from chaos. If you take a chaotic system, of course, it's very sensitive to initial conditions. So any very, very tiny change of the initial condition will change completely the output. And therefore, very quickly, the output will be random. So that's not too bad. You can use it. But there are still some issues with that. First of all, a system which is chaotic is only chaotic within a given range of parameters. The same system can suddenly become deterministic if you move a little bit the parameters. So somebody who is clever enough to tune the parameters of your system by, for example, an external influence, changing the temperature, putting some radiation or something, could actually manipulate your chaotic system and make it deterministic, and he could know what's going on. Another thing which is actually very important is, especially in the context of the quantum computer, is that once a chaotic system is still something deterministic. So if you have good mathematical techniques, you might be able to predict the behavior much better than you can do today. And this, of course, could be done with machine learning and artificial intelligence. As we know, they can find the needle in the haystack. They can look at this very large data and find out some kind of repetitiveness or something like that, which would lead to breaking the randomness you wanted to have. Therefore, using chaotic system is again a possible idea, but probably not the best one. Quantum is great, and I explained very briefly yesterday, because whenever you do a measurement, quantum mechanics is telling you you cannot predict the result. There is absolutely no way, if I prepare a qubit in a coherent superposition between 0 and 1, and then try to measure if it's 0 or 1, the result is random. And we now know that there is no hidden variable which can tell you what it is. There is no way you can predict the result of a measurement which is starting from quantum. At IIT Quantique, we use the one particular way, which is really looking at the photon distribution of a laser light impinging upon detectors. And that's the basic idea behind our random number generator. And if you haven't done so, I encourage you to visit us on our booth and see how small you can make the system using this kind of idea. So you can today make a very, very small system which generates randomness from quantum principle and have a very, very good entropy. Applications, as I said, are many, many. Basically, anytime you need cryptography, you should use randomness, and it can be used in all these kinds of applications I mentioned here. Now I want to focus briefly on, of course, I cannot not mention the fact that our quantum randomness source is small enough to be in a telephone. And again, if you want to see for yourself, come to visit us on our booth. It can also be used in connected vehicles, for example. And actually, it's interesting to realize that the demands on standardization and testing for this kind of application are actually very, very stringent. We passed the test for environment test for vehicle, which are actually harder than the space one I will mention in a moment. But the focus of the talk really is in space. So in space, as we all know, the main requirement is SWAP, size, weight, and power. Because the satellite is restricted in all of these, you need to make it as small as possible, as light as possible, and it shouldn't use any power if possible. So that's the first thing. Second thing, which obviously is a big difference between space and ground, is radiation hardened, because in space you have a lot of radiation and you need to test your system in order to make sure that it will work even when you have a lot of radiation. And the last one, which is a little bit the same, is harsh environment, which means that you need to work at very low, very high temperature, zero pressure, so on and so forth. There are many, many tests you need to do in order to be able to space qualify a chip like that. And that's basically what we did with our system. So we didn't do the chip only, because actually it's not really possible, but we put the chip on the board, and we tested the whole board for space, and we passed basically everything that was needed. Again, to make a space-qualified electronic board is not totally obvious. I mean, you need to follow some very strict regulations. Once you do that, you have a board which you can test. And of course, we went through all the tests in order to space-qualify this little board. And now with this board, you can safely take it, put it into a satellite, have a totally standard communication between the board and your computer or whatever you're using, and you can make sure that you have good randomness there. And again, it can be used for QKD, because you need randomness for QKD. It can be used for any kind of communication with satellite, and we have a major satellite builder, manufacturer, who is going to use this kind of system in his satellites. I just show here a little bit, but probably not too much, the test we were doing. So we took space qualification is a rather long and expensive process, and this is the reason why any space qualified board is rather expensive. I mean, something which you can sell for a few dollars in the ground will go to thousands of dollars, simply because you spend so much time and money doing all the tests to make sure that it will work. And our system obviously passed all that. So a summary, I think the most important thing is really to remember that whenever you do cryptography, classical, quantum, post-quantum, whatever it is, make sure you start with good randomness. Otherwise, your keys are worth nothing. In the quantum era, it's even more important, because we believe that the power of the quantum computer may actually be strong enough to destroy any kind of pseudo-randomness you have. If your randomness is not good enough, a quantum computer, machine learning, and artificial intelligence may actually be able to find in some way what's behind and actually extract then the keys, or at least get an idea of the key. Remember, if you have a key and somebody can get the first bit of your key, doing the same process over and over again, it will then get the second bit and the third bit. So even if you have a 256-bit key and you leak one bit, you basically leak the whole key. Okay, so that's very important to remember, that you really need something very good to start with. That's why we believe that quantum technology is really the best way to generate randomness. And with respect to this session, if you need randomness in space, you can already have space-qualified QRNGs now. They're available as I speak now. And this will improve security in your satellite by making sure the key you start with is good. Of course, it's up to you afterwards to make sure that all the rest of the chain is good enough. At this point, we are only talking of key generation. All the rest have to be done, and in order to get real security, you start with a good key and you need to make sure that all the rest follows. Thank you very much.
Pleasure to introduce the last speaker of this session, Professor Urbasi Sinha. She is a professor at the Raman Research Institute, Bangalore, and heading the Quantum Information and Computing Laboratory at RRI. She completed her PhD at Cambridge University, UK, on experiments in high-temperature superconductivity. Her scientific recognitions include the Homi Bhabha Fellowship in the year 2017, as well as 2018 ICTP-ICO Galliano DiNardo Award in Optics. She was recognized as one of Asia's top 100 scientists by the Asian Scientist for the year 2019, and has also been awarded the Simons Emmy Noether Fellowship at the Perimeter Institute, Canada. She also led the 2-member winning team as a mentor at the World Skills International Competition in Quantum Technology at the BRICS Future Skills Challenge organized by the Russian Quantum Center in Moscow. She also won the ASSOCHAM Women in Cyber Making a Difference Award. Professor Urbasi Sinha, please.
Thank you very much. So green button, yeah, to go forward, red button to go backward. Doesn't work. Okay, so thank you very much for the kind introduction, and of course thanks to TEC, CDOT and TSDSI for inviting me to present this talk here today. As was mentioned, I am at the Raman Research Institute in Bangalore, and I'm also an affiliate faculty at IQC and CQIQC and a Simon Seminoider Fellow, all in Canada. So I would like to thank my previous speakers for doing almost every introduction that I may have needed for my talk. So I can jump straight to telling you what we have been doing, over the last few years. So with that, this is what we work on. We work with photons. We work on quantum computing, quantum sensing, QIP, fundamentals of quantum mechanics, but today's focus is, of course, quantum communications. In a nutshell, this is what we represent. So here you can see our projects in quantum communication. So we are working on satellite-based QKD. This is India's first funded satellite-based QKD project, and I'll tell you over the next 13 or 14 minutes on this project. Having said that, we are also working under the DST Quest project on quantum relays and repeater technologies, DST ITPAR on integrated photonics-based quantum key distribution, as well as long-distance quantum teleportation and device-independent random number generation from a project funded through MIT. We are India's first lab dedicated to photonic quantum science and technologies, and we have many interests, including higher dimensional quantum computing and quantum information. So this is some of the snapshots. And this is essentially the main highlight results. The back button doesn't work as well as the front one, which wasn't going to be my... Madam Chairperson, please note that I've spent a bit of time going back and forth, okay? So these are the highlight results from the lab over the last couple of years, and of course I won't be telling you much about them. So having said that, this is how our journey began in December 2012 with various people who came and graced the occasion of inaugurating our lab. These are the people who are, of course, making things happen in the quantum communication space, and there are several more in other domains in the lab. Quantum experiments using satellite technology. So it is a collaboration between RRI and Indian Space Research Organization, particularly UR Rao Satellite Center and LEOS, which are both based in Bangalore. Our aim is rather simple. We want to establish information theoretically secure quantum communication over large distances using a satellite as a trusted node, and essentially perform entanglement-based quantum key distribution between two Indian ground stations using an Indian satellite as the trusted node. Now, why is this experiment exceptional? I mean, this is a rather objective view. Quest is India's first project on satellite-based quantum communications. As RP mentioned earlier, we didn't have a lot of traction to get funding for these projects till our neighbors actually flew a satellite. And so we benefited from that. And we started at a time when the field was not that popular. And its achievements, we believe, humbly, have played a major role towards putting India on the global quantum communications research. So I think, that makes it already exceptional. Having said that, it works on security in communications, which I need not introduce, and satellite is a good means. I think by now we all have an understanding of that. Having said that, this is the picture of two different possibilities towards satellite-based QKD. The left one is what our friends in China have done. They have demonstrated downlink-based QKD, and these are some publications from the group for that. So downlink means that the entangled photon source is in the satellite. Okay, so you fly it away. What we are aiming to achieve is uplink-based QKD, and having said that, this has never been shown before globally. So naturally, we are aiming to achieve that because really we like to stress ourselves out at RRI. So we want to do something which hasn't been done, so not repeat and so on and so forth, all those crazy things. And so, but what are the scientific aims of this? One, uplink allows for photon source to be at the ground-based lab. We don't need to fly it. So this means that we have more flexibility with changing the source even after the satellite has been launched. So Joyee comes up with a better source 1 year after the satellite is launched. We can in fact integrate that without having to fly another satellite. We can include quantum memory components after the satellite launch. And so essentially it gives us a tremendous scope for novel first-in-the-world science, but then it's also very challenging. Many challenges, like Bruno mentioned, many things have to be space compatible and some of them don't exist. But then we are very happy to take up this challenge, and we are sincerely hopeful that we will get there in real time. So this is, these are the things we have achieved. Development of a QKD experimenter simulation software. We discussed this in the panel discussion. We have done the performance analysis with an in-lab protocol. We have developed, of course, several entangled photon sources. We have also done free space atmospheric channel characterization, we were told. That is important, of course. So prototype for entanglement-based QKD, both in lab as well as atmospheric channel. And currently, we are very excited on our progress with the moving receiver platform for QKD. So, okay, this is, of course, the big picture. We'll skip that. The milestones achieved so far. So this is, of course, one of our very, important milestones. This was an in-lab experimental demonstration of the B92 protocol. And so this is India's first reported end-to-end free space QKD experiment, which has been published in an internationally peer-reviewed journal. And so we had competitive key rate and QBA, which were better than the previous ones. Then we went on to do the first demonstration of QKD between two buildings using an atmospheric free space channel. This was done in February 2021. We have heard of other demonstrations. Some of them also call themselves first, but that's not right. Ours was definitely the first in terms of the chronology. And we achieved this very beautifully. We are very proud of this. Very recently, we have done something which I'll talk about for a couple of minutes, which both RP and Joyee alluded to. We need to correct the polarization if we want polarization degree of freedom, and we have come up with a very interesting method to obviate that. And then we are also now becoming software developers. So we are developing software for simulating QKD with device and process imperfections, and so on. So this is the B92. I'll skip the details. It involves two measurement bases, but the idea is this is on Heisenberg's uncertainty principle. These are our, basically the components used. And having said that, at the Alice side, we used a heralded single photon source using continuous pumping, which kind of was an answer to the PNS type attack, which we could avoid to a large extent. Then we used passive quantum randomness. Within the setup, we used quantum random number generator so that we could obviate attacks based on active random basis selection. This is our Bob module. And here also passive quantum randomness, no gated detection required, and continuous record of timestamps. So these were some of the novelties we introduced, which made us achieve this higher key rate and lower QBA than all previous demonstrations. So there's the snapshots of the actual setup, of course. And going on to the next thing. So with QKD becoming commercially viable, advanced engineering techniques are being proposed. So direct testing is not always very cost effective. You don't want to build an optics setup and then realize you want to build it better. So a simulator can accurately pre-evaluate the performance of these setups and designs. So the competing QKD simulation toolkits in literature are these, and maybe you will find more if you search. But having said that, missing requirements in this are quick and precise simulation of physical processes, and consideration of experimental non-idealities. So we are developing software as experimentalists. So we know what problems we face, so we include that. So our results obviously will match better than the commercially available ones right now. And so this is what we call QKD Sim, QKD Experimentals Toolkit. We have created a logo with a lot of hope for the future. So these are the various details. So we are following the AGIFOL model of software development. And so we have also come up with a lot of nice post-processing algorithms as a part of this software development, which you can all, you can see the details in the publication that is listed below. You can see the beautiful match between theory and experiment here. And this is something you wouldn't get if you just used an off-the-shelf simulator. This was the previous result, and this was in fact held by a group from NASA. And so you can see that our key rate is much higher and QBA is much lower. In fact, ours is information theoretically secure and theirs wasn't. So this is our achievement. So it matches very well. Salient features, as I mentioned, different types of attacks could be mitigated. We also got a lot of appreciation for this. This is popular media. This is Nature India, which is a science forum. This is IBM blog, I would say an industry recognition. And this, the biggest one, Government of India recognizing us for our small efforts. So this is what resulted from this development. We have done in-lab quantum key distribution, of course, using entanglement-based QKD. And these results are actually going to appear. So this was accepted a couple of days ago, very much in time for the conference in Communications Physics, which is a very important journal from the Nature Publishing Group. And so we're very happy with these results. So this is our performance analysis. As you can see, this is our in-lab prepare and measure based protocol, and this is our BBM92 protocol. So clearly, we have achieved very competitive numbers in all these protocols. Having said that, As I said, I'll talk to you about this very recent result, which will be appearing shortly, about how we can obviate the polarization correction. So long distance QKD, polarization of light, is a commonly used degree of freedom, and it's becoming increasingly important. So significant challenge is, as was mentioned, that polarization gets affected due to birefringence in fiber-based as well as free space communications. So variation of reference frames due to satellite movement in long haul demonstrations. So conventionally what we do is active feedback based mechanism in real time polarization tracking, right? So what we employ is a polarization basis compensation method that obviates the need for active polarization tracking in satellite QKD. So we replace the active with a passive feedback mechanism, which works very, very well. And in fact, we are very happy, that it is independent of any local polarization rotation. So these are, this is the concept. So active feedback. So essentially you have to dynamically compensate for any polarization fluctuation. Robotized polarization correction has also been seen by many groups on active control system, but our approach is without active feedback. We perform a quantum state tomography, obtain the density matrix, evaluate the optimal measurement basis choice that leads to high anti-correlation, and then achieve the best trade-off between key rate, Q-bar, and symmetry. So this, I want to show you the results. So this is the one I really like. So you can see the blue dots. Those actually are measured in conventional measurement basis. So you can see as the fidelity drops with your state, this just shoots up, right? So it just goes really, really haywire. But then now if we use our method, you can see the orange dots. These are actually a flat line. So these orange dots are measured in our new technique of the optimized measurement basis. And we, have many more results in the paper, which you're happy to look at. I mean, if you are happy to look at them, I can discuss them later. So these are all the optimizations which have been done. But the main idea is that it works very well. It converts a really exploding graph into a straight line. Okay, and so usefulness is obvious. So we can correct this without having active feedback, no control systems required. It's also cost effective. Because, these usual ones are resource intensive and result in additional maintenance cost. Ours, will of course serve as an important tool in both fiber-based and free space communications. So having said that, I wanted to show you the, is this possible that I'm going back? Again, yeah. So I think this is working. Yeah. So you can see this is our free space demonstration. So from within the lab, we are actually projecting the photons from the ALICE side out through our telescope arrangement. This is the ALICE module, just to give you a bit of a lab tour. And so this is the ALICE module. So we come out of this window, and then we go straight across to our other lab, which is situated some distance away, and we have our Bob module. And this distance is 50-meter distance because RRI is full of trees. And we cannot really have a free space link without cutting down one. And that we cannot do. Our project will stop, institute will stop. So 50 meters is what we were limited to because of where we are. And of course, that is not an issue. So this was the atmospheric channel. And so these are our parameters. So you can see when we first achieved this in February 2021, we of course had lower key rate and higher Q-bar, but then we have done a lot of optimization after that, and now we have much better numbers and much more stability. But having said that, we did achieve this first in our country. And and then we went on to do something, partly inspired by all this discussion about 200 meter, 300 meter that followed, and partly also inspired by science. So we said that, let us actually simulate the effect of atmosphere over this channel and see if, even if we can't cut down trees, can we predict what would happen if we keep increasing the distance by taking the atmosphere into account. RP talked about atmosphere, he talked about, we have also not patented anything in this, but then we went on to do the simulation to see what would happen if we actually did that. And so this is, the kind of difference you would see, 200, 300, 500 even. It's not a very large drop in our atmospheric scenario. And so this is what we went on to do. We put filters at our source to induce attenuation in the photons and see how the key rate would drop as a function of distance. So as you can see, this is what we already had at 50 meters, but then with all those simulations, we calculated the attenuation required to simulate higher distances. So at this very important number now of 300 meters, which you keep hearing about, our drop is essentially 10.2 to 9.5. So it's hardly a drop. So whether you do this demonstration across 50, 200, 300, or even 500,
basically you're not achieving anything new. If you go to several kilometers, tens of kilometers, then yes, of course, it will drop and you need to do a lot more to get that back. But these numbers are just numbers. So achieving it in 200, 300 is not a bigger achievement than 50. And so we prove that now through what we do know best, which is science. And so this, of course, is there. So having said that, now what we are very excited by, the last 2 slides, is the next step that we are working on for the last 1 year. So we have done free space communication between 2 buildings, but my satellite is not going to stare at me from the orbit. It's going to move. I mean, of course, that's what we wanted to do. So if it moves, I need to keep pointing at it and tracking it, right? That is a very important step. How do you keep that line of sight and you keep maintaining the QKD link? And so that is what is called, the pointing acquisition and tracking system which you need to develop, so that that works in conjunction with quantum key distribution. So without that, of course, none of this is really going to be useful for satellite QKD. So we went about it in several steps. As you can see here, we have the, first thing, we use the 2 gimbal mirrors on a translation stage and a single beacon in a closed loop setup. So this is what you can see. This is the transmitter gimbal, which is stationed here, and the receiver one is moving. And I think, if you can look very carefully, and if my friends there are cooperating, you can actually see that this is a video where you can see things move, hopefully. We have been working on it since yesterday to get this video to actually work. Do you actually see movement there, my friends behind? Yeah, okay. So you can see that, this is my beacon. So we have to center it on the, photodiode. And then we have to keep doing this, back and forth feedback so that it remains centered. So this centering of this circle that you see is your indicator that you are in line of sight. And of course, a lot goes into this feedback mechanism, which we have painstakingly developed. But this is just to give you an overview from Delhi while we are in Bangalore. And so this was our first such, attempt, where we did a linear feedback. Then, we went on to this beautiful demonstration, where actually we have a circular motorized arm. Okay, this is my last slide. Circular motorized arm. So essentially on the left you can see this was done completely in-house. We have a great workshop. So they came up with, basically mimicking a satellite. So a satellite is not going to move linearly either. It's going to have a circular motion. So how do we correct for circular motion? And so that is the next challenge which we took up. And so this is what you see. Now you have to really pay your attention to this big thing here, which is actually moving, and it is not moving very fast, obviously, it's moving at a certain distance. And if you keep your eye on this little circle here, then you will see that, this guy, it's the same arrangement of trying to, get the beam back to the center of your camera. But then now this is actually moving in a circular track. You can see that, I think I can see it, I hope you also see it. So this is actually, so these are all things, of course, steps which lead towards the ultimate thing. It's not doesn't happen in a day. And so with the circularized, motorized thing was very much appreciated by our colleagues at ISRO as well, because this is basically like a little demo sitting within the lab. And so now I want to leave you with this very interesting slide here. And you should hear back from us in a day or two. And so with that, I would like to also say that we are a member. So we have done a lot of things in order to make this quantum useful. And so we are a member of, we are the founding partners of the JESDA Open Quantum Institute, which is in Geneva. And so I am a member of the Incubation Advisory Board and a task force member. Whole idea is to see if we can make quantum computing useful for, things that we may care about, like food, health, and so on. So these are the Sustainable Development Goals of the United Nations. So I'm personally actually overseeing this particular aspect, and I'm learning a lot. That what we do is not all useless, in some sense. So, so this is one of my little explorations which I wanted to share with you. So with that, this is what we all look forward to. So thank you very much.
Thank you, Professor Sinha. With that, we'd like to express our gratitude to all our distinguished panel for bringing to the table their knowledge, experience, and expertise. And may I request Mr. Shashi Mohan, DDG TEC, to kindly present a memento to the chair. A memento for our chair, Shri Sanjeev Agrawal, Member Technology, Department of Telecommunications. And now I request Honorable Chair to kindly present mementos to all our panelists. Professor Joyee Ghosh, Professor R.P. Singh, Dr. Bruno Huttner, is it with you already?
I don't know. You're giving me every time I talk.
Professor Urbasi Sinha.
I had enough. One is good.
Let's have a quick